During this section we're going to take a look at the structure of the atom and how that leads into different types of chemical bonding that exist in Chemistry Unit 2. Right, first of all, the structure of the atom is based on three fundamental particles: the proton, the neutron and the electron. We now know that all atoms are made up of these three particles, and that's pretty much accepted, and you will be expected to be able to draw the structure of an atom using these particles. Right, so what we've got is a central nucleus in which we'll see protons and neutrons, and then round the outside in shells we've got the electrons orbiting the nucleus. Now the key point at this stage is to notice that the number of protons and the number of electrons must be the same as each other, because protons are positive and electrons are negative. Therefore, if they're not the same, then the atom will be charged, and that's it's not what we want. We need the atom to be neutral. Right, now looking at this structure, it's the same as what we've seen on the previous slide, except we've highlighted the specific parts. So the proton, the neutron and the nucleus are shown, and of course the electrons that are going around the outside in shells are essentially arranged in different sort of orbitals, which we'll talk about later. Right, so first of all, mass and charge of the fundamental particles. In the exam you'll be expected to remember the mass and charge of protons, neutrons and electrons, and it's essential that you'll learn this table. Now the mass of a proton is 1, the charge is +1, a neutron has a mass of 1 and a charge of 0, and an electron has a mass of 0 and a charge of -1. So you need to know that table. There's a good chance it will be asked in one of the chemistry papers that you sit this summer. Right, atomic number and mass number. Now what you will see when you look on the periodic table is every single element has a symbol and then two numbers sort of alongside that symbol. Now the smaller of the two numbers, in this case with the carbon the 6 tells me how many protons there are, and it also tells me how many electrons there are as well. So in this particular atom of carbon, what we've got is that there are 6 protons and there are 6 electrons present in carbon. Now if I wanted to find the number of neutrons present in carbon, I would do the 12 take away the 6, which just so happens to give me 6 in this case as well. But the neutrons does not have to be the same as the protons and the electrons. So you can get different numbers of neutrons to protons in different atoms. But you need to be able to work out the number of protons, the number of electrons using the bottom number, and then use the top number minus the bottom number to give us the number of neutrons. Right, every element has its own definitive number of protons. For example, nitrogen always contains 7 protons, oxygen always contains 8. The only time this number will change is if there's a radioactive decay or some kind of nuclear reaction goes on. Right, okay, so we're going to pick a couple of elements from the periodic table in front of us, and we're going to show you what the nucleus would look like. So we'll start off with a simple one, beryllium, Be, and what you can see from this one is that beryllium has the symbol Be, and it has an atomic number of 4 and a mass number of 9. Now what that means is I've got 4 protons, and because the mass number is 9, the total number of protons plus the neutrons must equal 9. Well, I've already got 4 protons there, so I need to add to it another further 5 neutrons to get my total mass number of 9. And of course, that will then give me the correct number of protons and neutrons for beryllium. Right, I'll pick a more tricky example now, for example, sulfur. Now, sulfur has 16 protons, so we'll just click that up very quickly. Now that's quite a large number, and then 32 is the mass. Now remember, the mass is the number of protons and neutrons, so therefore there must be 16 neutrons as well, and that will then give me the mass that I've got here of 32. Right, one that often causes confusion is hydrogen. Lots of people make the mistake with hydrogen of giving it a neutron when it doesn't need one. So the proton number is 1, so it's got 1 proton, and the mass number is 1, and that means it's got 1 proton and neutron. So when you combine the protons and neutrons together, it gives a total of 1 for hydrogen, so therefore I don't need any neutrons because that mass number is 1 and we've already got 1 proton there. So if I added a further neutron now, that would give me a mass number of 2, which is incorrect. So therefore for hydrogen it just has 1 proton and 0 neutrons. Right, the next thing we're going to look at is electron configuration. Now, the rule with electron configuration is that you've got to know a couple of things about what number of electrons each shell holds. Now, looking on the diagram on the screen, you can see that the first shell holds a maximum of 2 electrons, second shell can hold up to 8, third shell can hold up to 8, and they're not shown on the diagram, but the fourth shell can also hold up to 8 as far as we're concerned at GCSE. So, the rule is very, very simple. You build up from the lowest shell first, and you can't move on to the next shell until the shell at the start is filled. So, for example, we'll show you now fluorine. Now, fluorine has got the numbers 9 and 19 associated with it. So the 9 tells me that fluorine has got 9 electrons in total. So what's going to happen, I'm going to put 2 electrons in the first shell, which gives me a total of 2, and then I need a further 7 in the second shell, and that's given me the total of 9. It would be incorrect of me to put 1 electron in the first shell and then try to put 8 electrons in the second shell, because you can't move on to the second shell unless the first shell has been filled. Now, instead of drawing the full electron configuration out like I have done on the left, you can use a sort of abbreviation or a shorthand, and 2.7 or 2,7 is a shorthand way of writing what you can see on the left hand side in the diagram. Right, if we look at another example, argon. Now, argon has 18 electrons according to the number on the periodic table, so therefore I'm going to put 2 in the first shell, then I'm going to stick 8 in the second shell, and then a further 8 in the third shell will get me my 18. And all you've got to try and do when you do this is total up the numbers and add them together. 2 plus 8 plus 8 must give me 18, and it does. And that is sort of that's nearly as tricky as you would get. I mean, calcium is probably the hardest you would get at GCSE, and that has 20 electrons as the numbers show there. And again, 2 in the first shell, 8 in the second, then a further 8 gives me the 18, plus 2 more to give me the 20. And as you can see, because the outer number of electrons is 2, that also tells me that calcium will be in group 2 of the periodic table as well. Right, now, what I want you to do very, very quickly is just to appreciate how the structure of the atom leads to the sort of numbers that we're seeing on the right hand side here. Now, I'm looking at the atom and I can see that this atom has got 2 electrons in its first shell and then 7 in its outer shell. So a total of 9 electrons means that it must be fluorine. Right, the next atom has 2 in the first, then 8 and then 1. And because of that, it's a total of 11 electrons, therefore it must be sodium. And then this one, 2 in the first and 2 in the second, must be beryllium, that gives me a total of 4. And then if we look at the final one, 2 in the first, then 8, then a further 8, all added together gives me 18 electrons, therefore must be argon. Right, this is what we should know so far. The nucleus is made up of protons and neutrons. It's positively charged because of the protons, and it's very, very dense because all of the mass of the atom is concentrated in the nucleus. Remember earlier we said that electrons have no mass, so therefore all of the mass of the atom is basically contained within that nucleus. And electrons are very small and light, they have a negative charge, and they are able to be lost or gained in chemical reactions, which we'll talk about in a little while. And finally, they're found in shells, and as you should know, the first shell is capable of holding 2, and all the other shells are capable of holding 8, and you can't move on to the next shell until the shell below it is filled. Right, I'm just going to mention isotopes very briefly. This does overlap a little bit with physics, All we're going to say on isotopes is that isotopes are elements that have the same number of protons, i.e. in this case carbon. Both these carbon atoms have 6 protons, otherwise they wouldn't be carbon, but they have different numbers of neutrons. So this one on the left hand side has 6 neutrons because it's got a mass of 12. This one on the right hand side has 7 neutrons and therefore a mass of 13. So an isotope is an element with the same number of protons but different numbers of neutrons. Right, so the first thing we're going to look at in the bonding section is how we get the sort of different types of chemical bond and how we know which kind of bonds we've got and what kind of properties they will have as well. So the first thing to sort of get clear is what a bond is. A chemical bond is a force holding together 2 atoms. So, for example, in the chlorine molecule that we've got here, they are joined together, the 2 chlorine atoms are joined together to make a chlorine molecule by a chemical bond. Again, in this bottom example, the 2 atoms, the O and the H, are joined together by a chemical bond as well. So different types of bonds are formed depending on the types of atoms involved. Now this is the most important part of the whole section on bonding. If you don't understand this, then you're going to find it very difficult to appreciate what kind of chemical bonding we're dealing with. So the golden rules are, if you have, for you to have ionic bonding, you need to have a metal and a non-metal joined together. For covalent bonding, it's when you've got 2 non-metals. And for metallic bonding, it's where you've got metal atoms only. So you might have 1 type of metal, or occasionally you might have 2 metals. But usually for metallic bonding, it will be 1 metal unless it's an alloy. Right, okay. Now, all bonds involve electrons and changes in the number of electrons. Now, the biggest problem students get is they know what we've said on this sort of slide here, that ionic bonding is metal, non-metal, and so on and so forth. However, in the exam, you get given a periodic table like this, and how are you supposed to know which part of the periodic tables have metals, which parts are non-metals? So what you have to do is you have to draw what we call a bat line. Now, a bat line is just simply a line running from boron down to astatine, hence the name bat. And what that does is it separates the metals which are now on the left to the non-metals which are on the right hand side. There's only one element in the periodic table that doesn't fit this rule, and that is hydrogen, and hydrogen is a non-metal, and you've got to remember that. So the bat line will allow you to differentiate between the metals and the non-metals, but hydrogen is a non-metal, and that's very important that you remember that, because hydrogen is present in an awful lot of compounds in chemistry that you could be asked questions about. Right, okay, so what kind of bonding? We've got a few different formulas on the screen now, and what I've done, I've worked out using the theory of ionic, covalent and metallic bonding, what kind of bonding is present in all these substances. So CH4, I know that you've got carbon and hydrogen, both non-metals, therefore covalent bonding. Mg, a metal on its own, metallic bonding. MgCl2, a metal, non-metal, ionic bonding. NH3, 2 non-metals, covalent bonding. And then AgCl, a metal and a non-metal, ionic bonding. So it is as simple as that really, provided you've got your periodic table which you get given in the exam, and you know the 3 rules from the beginning, you can work out the bonding in anything. And once you do that, life will get very, very straightforward in this exam. Right, okay, ionic bonding first of all. Now, we need to look at why substances want to make ions. Now, the rule is everything wants to get a full outer shell in chemistry. If it hasn't got a full outer shell, it will try to achieve that by losing, gaining or sharing of electrons. Now the first thing is an atom that loses electrons, generally it becomes a positive ion. And this is because it's got more protons than electrons. Think about that logically. We know that atoms are neutral and they have the same number of protons and electrons. However, if you lose some electrons, then you've got more protons than electrons, so you are positive overall. An atom that gains electrons will generally become negative, and that's a rule you've got to remember as well. And generally, if you look at the electron configuration, you can see whether atoms will gain or lose electrons just by looking at their configuration, and which is the easiest way for them to obtain a full outer shell. Atoms with a nearly empty outer shell will lose electrons. Atoms with a nearly full outer shell will gain electrons generally. Right, okay, so we're having a look at a few positive ions here. Now, these atoms at the bottom are all metals, and we've got their configurations, we've worked those out, and what we can see is lithium's configuration is 2,1, so it's got 1 in its outer shell, it's going to lose that 1 and it will become a lithium plus ion. Magnesium's configuration is 2,8,2, and it's going to lose them out to 2 and become 2,8 and have a 2 plus charge. And then aluminium is going to have 3 in its outside shell, so it's going to lose all 3 of those and then become an Al3 plus ion. Right, now looking in more detail at some of these, here we've got a sodium atom. Now its configuration is 2,8,1. Now if we look at that, we can see that its best way to get a full outer shell is to lose that outer 1 electron. So at the moment it's got 11 protons and 11 electrons. However, when it loses its 1 electron, it's still got 11 protons, but now it's only got 10 electrons, so it's got a charge of +1. Now what you'll notice on the screen is that we've put square brackets around the sodium now. And that square bracket indicates that it is an ion. So it's lost or gained electrons. If you ever see square brackets, it's telling you that it's an ion that has either lost or gained electrons to achieve the charge that it has now got. So the square brackets and the plus charge are there to tell me that the sodium has lost 1 electron, and that's why it's positive. Now if you look at magnesium, slightly different but similar in some respects as well. Configuration is 2,8,2, so it's got 12 protons, 12 electrons. As you can probably guess, it's going to try and lose the outside 2. And it does that to become a magnesium ion. If it's lost 2 electrons, it's now only got 10, so its total charge is now going to be 2 plus. Again, the square brackets indicate that it's an ion, and the 2 plus charge tells me that it has lost 2 electrons. And that's how I know how many electrons it started off with, just by looking at that charge. Right, negative ions are slightly different, but in many respects work on the same principle. If we look at chlorine here, its configuration is 2,8,7. It wants to gain 1 to get a full outer shell of 8, and it does that to become 2,8,8 and has a minus charge. Oxygen has the configuration 2,6. It needs to gain 2 to become O2 minus. Now there's a slight mistake on the slide here. It's saying the oxide ions configuration is 2, when in reality it will be 2.8, because it's gained 2 on top of that 6 in order to get its outer shell of 8, and that's why it's got a charge of 2 minus. And then nitrogen, outer shell has 5 electrons, it's going to gain 3 and become 2,8. Again, there's a mistake here, but when it gains its 3, it's going to have a 3 minus charge. Now the other thing to notice is that when chlorine, oxygen and nitrogen become negative ions, their name changes and they end in "ide." Generally, chloride, oxide, nitride, all of those ions are negative ions generally. So looking in more detail at these, we'll take fluorine. Now fluorine has 7 in its outside shell, it wants to gain 1. So what we do is we show dots at the start and then a cross to show that it's gained that cross from another atom. It started off with 9 protons and 9 electrons, now it's got 9 protons and 10 electrons, charge is -1, again square brackets because it's an ion. Now if we move to sulfur, as you can probably guess if you look at this one, configuration 2,8,6, it's going to want to gain 2, and it does that, and it gains 2 to become a sulfide ion. Charge is now -2 because it's gained 2 electrons. So as you can see, if an atom loses electrons, it becomes positive. If it gains electrons, it becomes negative. And once it's gained or lost electrons, we put square brackets around it to make sure that people know that it is now an ion and it hasn't got the same number of protons as it has got electrons. So every group in the periodic table has its own unique charge. So group 1 has a charge of +1, 2, +2, group 3, +3. Group 5 takes a charge of -3 because it wants to gain 3 electrons. 6 will always be -2, and 7 will always be -1. Now if you know that and you've got your periodic table in the exam, you can pretty much work out the charge of any ion that's there. Right, so we'll just take a look at a couple of example elements here. Now we've given you 5 different elements. Now all of them, we've wrote the electron configurations down. The first thing I want you to realise is that you have to pick the most appropriate way that these elements will get a full outer shell. So if you're calcium with the configuration 2A82, you're going to lose 2 electrons. Therefore your charge is going to be +2. Hydrogen is unusual. It can be able to gain 1 electron to get, because remember the first shell only holds 2 electrons. So if you've got 1 in your first shell, you can gain 1 to get the full outer shell of 2, or hydrogen can lose 1. So hydrogen is actually unique in the sense that it can become +1 and -1. But for simplicity's sake, we'll assume it's +1 for this. Phosphorus 285, hopefully you realise, will become a -3 ion. Fluorine 27 will become a -1 ion. And beryllium is 22, will lose that outer 2 and become a +2 ion. Right, the next part we need to look at is just briefly about compound ions. So now and again you will get ions that are made up of 2 different elements, and these exist, and these are the ones that you would do well to learn. There's the hydroxide ion, which is OH-, sulfate ion is SO4 2-, nitrate NO3-, carbonate CO3 2-, and ammonium NH4+. Now it doesn't matter, you don't have to actually memorise the whole lot of these. You are given them in the data sheet on the back of your periodic table for use, but all you would be aware of is that they do exist and you don't have to have elements on their own. You can have combinations of elements which can also form ions as well. Right, ionic bonding itself. So the metal joins to a non-metal and they make a ionic bond. We're going to look into more detail about why that happens, but generally the electrons are transferred from the metal to the non-metal, and we get then an electrostatic attraction called ionic bonding. So we're going to start with sodium and chlorine. Now if you look at sodium, we know that it wants to lose an electron. It's got 1 in its outer shell. If you look at chlorine, you know that that wants to gain 1. So what happens is sodium loses an electron and chlorine gains that electron, and what you get is a positive and a negative ion that then attract each other to form an ionic bond. And that attraction is very, very strong. It's an electrostatic attraction, and it's formed obviously because the charge of sodium is plus and the charge of chloride is minus. And this electrostatic attraction is known as our ionic bond, and it exists in all ionic compounds. Right, so we're going to take a look at a couple of examples of our ionic structures, starting with sodium chloride. So when we look at the actual sodium atom and the chlorine atom, you can see that the electron configuration is shown. For sodium 281, for chlorine it's 287. Now looking at that, it's easy to see now that the sodium wants to lose an electron and the chlorine wants to gain 1. So that's what's going to happen. The electron from the sodium will make its way across and join onto the chlorine. Now straight away we put square brackets around them to indicate we've now made ions. Now the sodium is a +1 ion because it's lost an electron, chloride is a -ion because it's gained 1. And what happens now, because they are now charged, these ions will then attract each other electrostatically, and that will form an ionic bond. Now the problem with ionic structures is they do not exist as individual sort of molecules like you're seeing on your screen there. What happens is many ion soluble come together to stack into a giant ionic lattice. So it's incorrect for me to refer to an ionic structure as a molecule because it doesn't exist as a molecule. What happens is it exists as an ionic lattice, which is a three-dimensional structure containing millions upon millions of ions stacked into a three-dimensional cube structure, as you can see there. Right, so the next part is to look at the formula of ionic compounds. Now this can cause confusion quite simply because people don't understand how to work them out. Now in the exam itself you get given a table, a data sheet with all of the ions charges on it. Now what we need to show you is how you use that information to work out the formula of an ionic compound. Now we know that sodium is Na+, and I know that oxygen or oxide is O2-. Now the key to this is you've got to make it so the charges balance. So originally the sodium has a +1 charge and the oxygen is 2-, so we need the same number of pluses as minuses. So if I've got a 2- charge and I've only got a sodium with a 1+, I'm going to need 2 sodiums. So now if you look on the screen, I've got a total charge of 2+ and a total charge of -2, and that is because they are now balanced. The formula will work out correctly. If I'd have just had 1 sodium and 1 oxide, it wouldn't have worked because I've had a +1 charge and a -2 charge, and of course they're not balanced. So the formula of sodium oxide is Na2O, and that's wrote down there. And generally you always write the positive ion first. Right, another example would be magnesium chloride. Now magnesium is a 2+ ion and chloride is a -1 ion, so I'm going to need 2 chlorides to balance up the 2+ charge from the magnesium. Because magnesium's 2+, I need the total charge of the negative side to be 2-. I can only achieve that by having 2 chlorides, so therefore my formula is MgCl2. Again, I'm writing the positive ion first. Right, a more tricky example now, aluminium and bromine. Aluminium's a +3, bromine is a -1. So if you want to just pause the video, we'll give you a moment and see if you can work out the formula for aluminium bromide. Right, hopefully you've worked that out to be AlBr3. Again, we need 3 Brs because they're -1 and the aluminium is +3. So I need a total charge of -3, and I can only achieve that by having 3 bromides. Right, aluminium oxide. Aluminium has a charge of +3, oxide -2. So if you want to just pause the video and see if you can work out the formula of aluminium oxide. Right, hopefully you've been able to manage that the charges are not going to be able to be balanced by just doubling one of the atoms. We're going to have to change both of them. And what we do is we put 2 aluminium ions and 3 oxide ions, and that gets me a total charge of +6 on the aluminium and a total charge of -6 with my 3 oxygens. So my formula becomes Al2O3. Right, now here are a series of elements that are going to bond together, and what you've got to do, if you just want to pause the video in a moment, write down this table with all the charges of each element above and the ones on the side, the negative ones, and try and work out the formula. The first row, we've done that for you, and we've worked out all those formulas. If you want to pause the video now and see if you can work out the rest of them, we'll reveal the answers in a little while. Right, hopefully you've had a chance to work all of these out. Obviously we haven't got time to go through every single one of them, but if you just want to check your answers, say pause the video now and just check through your answers and see if you've got them all correct. Right, the next one is using compound ions. Now again, compound ions I mentioned earlier are ions where you've got 2 elements in the ion. So here we've got NO3, which is a compound ion. Now, the charge on lithium is +1, the charge on NO3 is -1. Both of those bits of information will be on your data sheet in the exam. And what I'm hoping you're going to realise is that ratio is going to be 1 to 1. So the formula is just going to be LiNO3. Now, they've put brackets in here, but you don't really need the brackets, to be honest, because we're not doubling anything. We only usually put brackets if we have to multiply a compound ion by more than one of them. So if I needed 2 or 3 of them, then I usually put a bracket and then a 2 or a 3 at the end. But in this case, we don't need that. Right, our next example is magnesium nitrate. Now, magnesium's a 2+ and nitrate's -1, so I'm going to need 2 nitrates to balance up my magnesium. And I can't just put a number 2 after the nitrate. I've got to put the nitrate in brackets because it's a compound ion. So the formula is going to be Mg open bracket NO3 close bracket with a 2. And the reason why I've needed the brackets is because there are 2 elements present in this ion, so I need to bracket them all and put a 2 to make sure that I haven't made any errors in my formula. Right, the next one is sodium sulfate. Sodium +1, sulfate -2. Again, that will be all that information will be on your data sheet in the exam. I'm going to need 2 sodiums to 1 sulfate. So therefore my formula is going to be Na2SO4. I don't need brackets this time because I'm only doubling the Na, and that's not a compound ion, it's only got 1 element, so I can just put a 2. If I wanted to double the SO4, like is done down here, I would have had to put the brackets and then a 2 because it's a compound ion. Right, finally, ammonium sulfate is quite a tricky one. Again, both charges will be given to you in your data table. Ammonium +1 and sulfate -2. We're going to need 2 ammoniums to balance the sulfate up. And because it's a compound ion with 2 elements, I'm going to need brackets around it. So that there would be the formula that I will be looking for. Right, this is sort of the nitty-gritty now, properties of ionic compounds. This is the bit where you're going to get some big marks, hopefully, if you've learnt your material well. Now, in an ionic compound, we know there are millions and millions of ions packed together into this nice cubic lattice arrangement, and the ionic lattice continues in this way. The word we use to describe it is lattice. The words that you cannot use are molecule, macromolecule, covalent, metallic. Any of them phrases, if you use them when you're talking about an ionic structure, the examiner will mark you down for doing that. So the first property that we're going to look at is the idea of the ionic lattice and its melting points. Right, so we're going to look at the ionic lattice and its melting point. Now, the first thing to notice is that ionic bonds are very, very strong. They're strong electrostatic attractions between oppositely charged ions. So in the exam, you must use that phrase in bold red. The strong electrostatic attraction between oppositely charged ions. That is why the melting point of anything that's ionic is very, very high, because the positive and the negative ions attract each other with this electrostatic attraction, and it's very, very strong. A couple of examples of melting points there, and you can see that they're both quite high melting points. Right, the next thing is the conductivity. Now, if we try sodium chloride solution, then you can see that it conducts electricity quite well. If we try sodium chloride liquid, that conducts electricity quite well. If I try sodium chloride solid, that doesn't conduct electricity at all. And we need to be able to explain why that is. Now, if we take a look at the structure of solid sodium chloride, the ions are fixed and they cannot move. So, because the ions can't move, it can't conduct electricity. However, if we look at the molten or liquid sodium chloride, then the ions are now free to move. So then the molten or dissolved sodium chloride can conduct electricity because the ions are free to move. In this case, when you're dealing with ionic structures, it is incorrect to start talking about delocalized electrons. It's nothing to do with delocalized electrons. Ionic structures will conduct electricity if the ions can move. If the ions can't move, i.e. solid state, then it won't conduct. And as a general rule, ionic compounds are soluble and usually dissolve quite well in water. Right, ionic compounds are brittle. This is easy to explain, but if you were doing this in the exam, I'd make sure I drew the examiner a diagram. Now you can see the nice strong interactions shown on our ionic lattice there. If we provide a force and move those ions along one, then we create a repulsion because the positive lines up alongside a positive and the negative lines up alongside a negative, and they then repel each other, and it causes the ionic lattice to shatter. So ionic substances, although they have high melting points, they are brittle, and that essentially means that there's no flexibility. If you try to bend them, they'll just crack, and if you hit them, they'll just shatter. So that is ionic bonding. Here are a series of 6 quick true or false sort of statements. If you just want to pause the video, write them 1, 2, 3, 4, 5, 6, and just put true or false, and check your answers in a second. Right, hopefully you've done that, and here are your answers. If you just want to check those off, and hopefully that'll give a good indication of whether you've understood what we've discussed. Right, for metallic bonding, we've essentially got a positive metal ion, and this is surrounded by a delocalized sea of electrons. Now this forms a regular lattice structure in the same way that an ionic lattice is formed, but this is a metallic lattice. If you notice the difference, in a metallic lattice, all of the ions in this one are all positive. The negative delocalized electrons surround the metal ions, and your metallic bond is the attraction between the positive metal centre and the delocalized sea of electrons. And that's very, very important because when you're asked what is a metallic bond, you need to be aware that the positive metal ions attract to the delocalized sea of electrons, and that's where the bond actually comes from. So examples of metallic structures, there are many of them, but I've just picked a few from the periodic table. It's just any element that is a metal, so magnesium, copper, silver and sodium, all of them have metallic bonding because they're metals on their own, and therefore have metallic bonding. Right, in terms of properties, you need to be able to explain first and foremost why metallic structures have high melting points. So in this particular case here, we've got the metal centre, which is magnesium, and it's got a positive charge, and then you've got the little blue delocalized electrons surrounding it. Now what the animation is trying to show here is that as you heat it up, you are trying to break the attraction between the positive metal centre and the delocalized electrons. And the problem is this is very, very strong, and therefore requires a large amount of energy to break. So most of the metals will have high melting and boiling points because metallic bonds are strong, and you have to break the attraction between the positive metal ion and the delocalized sea of electrons. You've got to use those phrases in the exam. Right, next up is conductivity. Metals are good conductors quite simply because they have delocalized electrons. This means the electrons are free to move through the structure, and therefore all metals will allow electricity to flow as a result of these delocalized electrons. The delocalized electrons will also allow the metals to be good conductors of heat as well. Now the final property is malleability and ductility. Now many people don't know what these phrases actually mean. First of all, if something's malleable, it means that if you hit it with a hammer you can shape it into different shapes, a bit like an ironmonger would do many years ago. And if something's ductile, then that means you can stretch it and it will pull and stretch until you can make it into a wire. A little bit like, for example, a curly whirly bar. When you stretch that, you would describe that as being a sweet that is ductile. You can stretch it into shape. Now the reason why pure metals are malleable and ductile is because the ions are similar sized, so they can slide over each other easily, and this allows metals to be hammered into different shapes and also to be extended and pulled into wires. So for metallic bonding you need to be able to explain these three properties. You need to make sure you can explain why the melting point and boiling point is high, why they're good conductors, and why they're malleable. As well as that, you need to be aware of the general structure shown on this slide here with a positive metal centre and the delocalised sea of electrons, because you could be asked to draw that in the exam. Right, the next part is alloys. Now when you have a pure metal, like the one shown at the top, all of the ions are the same size, so they can slide over each other very, very easily. This makes pure metals very, very soft. If you had a gold ring made of pure gold, then it would be too soft to actually make it useful, because whenever you knocked the ring it would just bend and dint, and essentially your jewellery would be ruined within a few days. So what happens is metals generally are alloyed, which means they're mixed with other elements. It might not be other metals, but it can be other metals as well. And what that does is that creates a structure where you've got different sized atoms. When you get that, the atoms can't slide over each other as easily, so therefore an alloy is harder than a pure metal. And that's why gold rings, for example, have carat ratings, because they're alloyed with the different metals to give different effects. The final thing to be aware of with an alloy, although alloys are stronger, they can't be shaped as easily and they're sort of harder. Their drawback is the more of an extra elements you add other than the metal, so the more other elements you add, the more brittle the metal alloy then becomes. So if you add lots and lots of other elements alongside the pure metal, then you can essentially make it very, very brittle and subject to cracking, which means the metal can break. Right, just a quick look here that we just want to be aware of comparing ionic and metallic crystals together. Now I've set this up, and all I want you to be aware of here is just a summary of both types of bonding that we've looked at during this section. So they're both lattices. The ionic one is positive and negative ions, the metallic one is a positive ion surrounded by delocalised electrons. Both have high melting points. Ionic substances are brittle, whereas metals are malleable. In ionic substances, when they're solid, they don't conduct because the ions can't move. In a metallic lattice, they do conduct because they've got delocalised electrons. And in the ionic liquid or dissolved, then it will conduct because the ions become free to move. If you melt a metal, it will still conduct as well because of the free electrons being present. So make sure you know the difference between ionic bonding and metallic bonding. Ionic, metal joined to non-metal; metallic bonding, metals only. Right, nanotechnology is the study of extremely small substances called nanoparticles. Now, in the exam, you would be expected to know that nano means very, very small. It's actually a Greek word which means dwarf. And the key definition in this section is that nanoparticles are 1 to 100 nanometers in size. So in the exam, if you're asked what is a nanoparticle, you need to say it's a particle which ranges from 1 nanometer to 100 nanometers in size. Now that is pretty small, but that's the definition of it. Now the next section is to look at how these nanoparticles are useful to everyday life. Now the first thing that you might be aware of is sunscreen. Now sunscreen is made up of nanoparticles of zinc oxide and titanium oxide, and these obviously protect the skin from harmful radiation. Other examples of nanoparticles are things such as plasters and bandages, which contain tiny, tiny nanocrystals of silver, and the silver is toxic to bacteria, so it keeps the wound from becoming infected. And you've also got athletes' socks, sometimes have a silver coating woven into their fabrics on the nano level, and that kills bacteria, which basically makes your socks smell. Other examples are fabrics, which can repel stains, and the other one, which is quite unusual, is self-cleaning glass. This is a new idea, and we'll just quickly go through how this works. Generally, what happens is scientists coat the panes of the glass with tiny layers of titanium dioxide, and that forms a coating on the surface of the glass. And then what happens, the glass itself essentially becomes activated with the heat and the light, and then when dirt accumulates on that surface, because it's so smooth, when the light gets on that layer, it breaks down the dirt, and then as the rain comes in, rain droplets sort of wash off the sort of debris that was there previously. And the idea is that you don't need a window cleaner. Now, of course, this is not particularly any good for health. It's just a cosmetic idea that you don't have to clean your windows. But again, it's just a use of nanoparticles. So hopefully we've given you a bit of an idea of why nanoparticles are useful. The big thing for nanoparticles as well is the dangers. Now, no one mentions this, but people are quite concerned because nanoparticles have such a high surface area. Then people are concerned that it would make them very, very effective and dangerous in terms of if you were using nanoparticles and there was a spark in the factory, there could be an explosion. The other problem is the risk of them finding their way into the air and us breathing them into our lungs and becoming problematic in that sense. And of course, if you breathe tiny particles into the lungs, they can cause potential lung problems in later life. So these are just areas of caution to be aware of. The nanoparticles do have potential safety risks that we need to take into account when we're using them.